Sure.
Hello, everyone, and welcome to another stellar seminar on radio astronomy. And today we have our speaker, Puja Majee from National Center for Radio Astrophysics, Tata Institute of Fundamental Research in India. Puja is a PhD student of Professor Divya Oberoi, and she's working on solar radio astronomy. So today she will tell us about probing the magnetized corona with type 2 solar radio bursts. So thank you. Take it away. By the way, okay, I can see your Tata.
Sorry, you're saying something.
Yep. And now it's black.
Okay. Okay. Can you see my screen now?
Yes, I can.
Okay, sure. Hello, everyone. I am Pooja, and thank you for being here. And so today I'm going to talk about how type 2 solar radio burst can be used to probe the um, magnetized coronal plasma. So corona is basically the hottest and the outermost layer of the solar atmosphere, which has a very ever-evolving magnetic field structure. So now this coronal magnetic field are basically the primary engine for all solar activity that is happening, and the so the geoeffectiveness of the solar eruptions or this activity, such as coronal mass ejections or flare, which are one of the main potent driver of the space weather around the Earth, which is so these are basically their geoeffectiveness are driven by this magnetic field, the coronal magnetic field, and therefore it is very important to understand the coronal magnetic field and both globally as well as the local magnetic fields. So that is what we are trying to do here with type 2 solar radio bursts. So let's start with an introduction to this type 2 solar radio bursts. So what are these? So these are signatures of shocks. So whenever there is an eruption, let's say a CME or flare, it basically drives a shock into the coronal plasma, and therefore then this shock accelerate the non-thermal electrons in the ambient medium, and then these non-thermal electrons excites this Langmuir wave, which converts into these plasma emission at the fundamental and the harmonic of the local plasma density. So what do I mean by that is that, so two important things is that one, these are plasma emissions which are related to the local plasma frequency, which means the local electron density, and these appears in the at the local plasma frequency and its harmony. And therefore, if you look at the right side, so this is how a type 2 solar radio burst look like. So this is the dynamic spectrum, and you will always see the fundamental and the harmonic emission. So these are the two emissions that you typically see. Now, as I said, these are signature of shocks. So as the shock propagates through the coronal plasma, it basically encounters lower and lower electron densities, and therefore lower and lower plasma frequency. And hence, with time, the type 2 appears at lower and lower frequencies. So therefore, this drift that you see here, which is basically telling you that the shock has propagated through the solar corona, and therefore you see this drift. And now if I estimate the drift of this type 2 emission, I can get an estimate of the shock speed. So each of these fundamental and the harmonic emission also shows substructures. So when each of these emissions are splitted into two lanes, they are called as band splitting. When there are more than two, they are called as multi-lanes. Now, each of these emissions also shows a lot of fine structures. How do they come? So when the shock propagates, when it interacts with the inhomogeneous medium, inhomogeneous densities in the coronal plasma, these fine structures of short time scale and short band appears as a result of this interaction between the shock and the inhomogeneities in the plasma. So therefore, if you characterize these short-lived and narrow-band fine structures, you can get an estimation of the spatial length as well as the spatial length of the inhomogeneities in the coronal medium. And also, typically, the fundamental emission starts from hundreds of megahertz, and which corresponds to a coronal height of, let's say, lower than 2 solar radii. And also, it can end up to few kilohertz, which is inner heliosphere. So as I said, these plasma emission can be used to prove the magnetized coronal plasma, starting from very like inner corona, lower corona, all the way to inner heliosphere. So therefore, these emissions are very, very important. Yeah, don't compare the frequency here because this is a very high frequency type 2 burst. So now let's talk about the polarimetric properties of type 2s. So why are they important? So polarimetric properties of type 2s can give you estimation, of the local magnetic field strength at the location of the shock. As you know that it is very difficult to estimate the magnetic field above 1.5 solar radii because at this height Zeeman splitting doesn't work, and also like estimating the magnetic field from heliopolarimetry also doesn't work here, and there are very few probe which can be used to measure the magnetic field at this height, and type 2 emissions are one of them. Not only that, polarimetric properties of type 2s can also give you insight about the underlying physical mechanism. Now, what do we know about these type 2 emissions? So as I said, these are plasma emissions. So there are theoretical expectations which says that the fundamental emission is strongly circularly polarized and the harmonic emission is weakly circularly polarized. Whereas if you go through the literature, there is a diverse range of polarimetric properties reported for these type 2 emissions, starting from unpolarized, weakly polarized. Sometimes people see harmonic emission to be weaker polarized as compared to the fundamental one, which is also expected, but there are reports which sees the other way around. But most of the time, I mean almost all times, the fine structures are observed to be more polarized as compared to the burst continuum. Another thing to note here is that all of these reports are done for the circularly polarized emission. So circularly polarized emission has always been reported for this type 2 burst, and there is no report of the linear polarization from these bursts so far. Another important thing here to note is that majority of these studies are depending on the dynamic spectrum, which means when you uh, observe the sun as a star, which means you no longer have any information, the spatial information. Now you might know that the polarization properties can both be positive as well as negative. And also at the same time, there can be multiple active region or multiple events which are occurring on the solar disk. And therefore, if you integrate all this information, you may end up with the information which is not accurate, and therefore now if you try to estimate the magnetic field strength from it, which will not be accurate enough. So therefore it is very important to do imaging studies, spectro-polarimetric imaging studies, which will give you the spatially resolved information. So that is what we have done here. So for that, we have used the Murchison Widefield Array, MWA, which is a SK-low precursor, which is located in Australia. And as you can see here, this is how one tile of the MWA looks like. So these are 16 dipoles, 4 cross 4 located in the 4 cross 4 grid. And the observing frequency is 80 to 300 megahertz. So there are different phases of MWA. So currently there are 256 elements which are located, when I say element, which means this one tile, which are located within a footprint of 5 kilometer. And currently it can generate 0.25 second resolution data. Also, it can go up to 10 kilohertz. But the data that we have used, or the event that we have analyzed here, was taken during the phase 1, which means at that time there were 128 elements. The maximum baseline was 3 kilometer, and which could give us like data at a rate of 0.5 second and 40 kilohertz. So now, why this interferometer is very important here? Because as you have seen that there are many elements within this small 3 kilometer baseline, which means that when you look at the instantaneous UV coverage, so this instantaneous UV coverage is very, very dense, which means now you can make high fidelity snapshot images. Why snapshot images are important here? Because as you have seen already, the type 2 burst has a lot of variability with time and frequency. It shows a lot of fine structures. So therefore, if you want to capture all this information all together, you need to make images with a very fine time and frequency resolution. And therefore, this telescope was very, very important and for us for this study. Now, let's go into the event that we have analyzed here. So this is the event. So as you can see in the left hand side, you see a CME eruption, and this was also associated with the M-class flare. And this event gave rise to this beautiful type 2 burst. So this is again observed by Learmonth spectrograph, Learmonth, and as you can see, this is the harmonic emission, this is the fundamental emission, and these 6 spectral boxes that you see here, so these are the different spectral band in which MWA has observed the type 2 burst. So MWA has different configuration in which it can observe. So it can observe continuously across this 30 megahertz, or you can split the bands or keep the bands in a discrete manner across this 80 to 300 megahertz. So for this observation, they were discretely configured. So as you can see here, so these are the 6 spectral bands which was only observing captured the harmonic emission. And if you see here the lower panel, so these are the 6 spectral band in which MWA has observed the harmonic emission. Now, I will not go into the calibration and the data analysis, calibration and imaging, but we can certainly go deeper into that. I'll mostly focus on the results part. So let's look at some of the images. So for this event, what we have done is that we have made full Stokes images with a frequency resolution of 160 kilohertz and a time resolution of half a second. And these are one of the images. So this is the Stokes I, Q, U, and V image. The circle that you see, this is the optical sun, and the ellipses are the PSF of each of the image. Now this time corresponds to when there was no, before the occurrence of the type 2 burst. And as you can see here, so there are two bright active regions which were located at the same time. And if you look at the Q and U images, it mostly look like the noise. If you look at the Stokes V image, there are significant amount of Stokes V emission from this active region, which was giving, so at that time, there was a type 1 noise storm associated to this active region. But the lower one, which was associated to the type 2 burst, there was no emission in the Stokes V. So now if we look at the location of these, so these are again, I just said that these are the 2 active regions. Now let's look at the type 2 burst. So this is the image of the type 2 burst. So as you can see here, the Stokes I image, the flux density has increased by 3 to 4 order of magnitude, and therefore you no longer see the other type 1 emission, the type 1 noise storm burst. And so this is the Stokes I. And if you look at the Stokes Q and U images, you do see high SNR signatures, positive and negative, in the location of the type 2 burst. Now, also we looked at the Stokes V images. If you see here, there are also high SNR signature of negative and positive. For this particular timestamp, the positive signature is not very prominent, but I'll show you other timestamps where we do see Stokes V signature as well, V positive signature as well. So these images basically tells us that yes, this type 2 has traces of linear polarization from it. And also, while people have been expecting the circular polarization to be always in the O mode, we also do see the other signatures. So there can be dual polarity signatures as well. So what we did is that we started characterizing each of this linearly and the circularly polarized emission. And let's start with the circularly polarized emission. So yeah, so this is the spectrotemporal variability of the circularly polarized emission. The left side shows you the negative circularly polarized source, and the right side shows you the positively circularly polarized source. And as you can see here, the negatively circularly polarized fraction goes up to 8%, which shows us that this has a very weakly circularly polarized emission, which is again, we expect the harmonic emission to be weakly circularly polarized. So it's fine, but when you go to the positively circularly polarized emission, the positive signatures, so the fraction goes up to 4%, which says that the negative one is more dominant. And also, if you see here that at the higher frequencies, the positive has uh, like positive polarity emerges exclusively at the higher frequencies, but we don't see much at the lower frequencies. So what we started doing is that we started looking at the morphologies of the sources. So as you can see here, these are the three different frequencies. And okay, so let me tell you what is each panel shows. So this is basically the what do you, the vertical yeah, so this xy plane is basically the sky plane on top of which, so basically one image, there are multiple images which has been stacked with time, and therefore this is one image, this plane, and while the z plane is basically the time. So with half a frequency, half a second resolution, all the images has been stacked together. So the upper row is basically the Stokes I, and the lower one is the Stokes V. So if you look at the colors, so here the blue one are the negative negative polarities, and the red one are the positive polarities. So as I said, these are the three different frequencies which are shown here with the red colors. And if you see in the Stokes I emissions, you would see variability in flux, also source, but that is again higher in the high frequencies. But in the low frequency, it's not much variable, it's quite stable. But if you look at the Stokes V emission, you will see uh, at the low frequencies, there are significant variability in the absolute flux, but there is no polarity change. But if you look at the higher frequencies, and here it is very, very prominent, which shows that there was initially one negatively polarized source, negative signature, and after that there was another positive signature which emerged, and then it converted into negative, and then again into positive. So there were even one single source is also changing its polarity with time. Now, if you look at the highest frequency here, you will also see that there are many times where this source, which is the type 1 noise term, which is associated with type 1 noise term, this source is comparatively higher as compared to comparable as compared to this type 2 burst. So now you can imagine if you just integrate all this information together, it will automatically lead to an incorrect measurement of the Stokes V. So what we tried to do is that we estimated the magnetic field strength from these images. So what we did is that we took the negatively circularly polarized negative signature, and we estimated the magnetic field strength. And then also again we estimated the magnetic field strength by integrating all these signature, and then tried to estimate the magnetic field strength, and then compared both of them. So this plot basically shows you the the ratio between the magnetic field strength from the images and the magnetic field strength which comes from the integrated information. And as you can see here, that the in magnetic field strength which was estimated from the images are always higher as compared to what we get from the integrated information. So which demonstrate that dynamic based studies may underestimate the magnetic field strength when multiple active regions are occurring, multiple active regions are present, or there are multiple polarity regions present. And these information or these magnetic field strength information are very important when we are using them to provide constraint on the coronal magnetic field models. So, okay, with that, we now will change our path and we'll look at the, oh, okay, sorry. Before that, I'll also try to show you the spatial variability of the magnetic field strength. So, this is again the same three frequency bands. So, and each of these bands, so each of these columns are basically the timestamp corresponding to the each frequencies. So, this is again the 80 megahertz, 120 megahertz, and the 132 megahertz at different times across the solar burst. And the color is showing you the magnetic field strength. So if you look at here, that each of the panel, you will find that the magnetic field is varying across extent of the type 2 burst. And also you will find always that the type 1 noise storm has a higher magnetic field strength as compared to the type 2, which is expected because we know these are coming from the coronal loops. But if you again look at the, as I said, that these are plasma emissions, so the higher frequency is coming from lower height and the lower frequency is coming from higher height. So therefore, at the lower height, which means the higher frequency, we should see higher magnetic field strength. And at the lower frequencies, we should see low magnetic field strength that we don't see here. Now, what could be the reason for that? It's because the magnetic field strength, the way we estimate it, depends on the local magnetic field strength, the plasma frequency, as well as the angle between the line of sight and the magnetic field. And this is the parameter which can smoothly vary even across the spatial extent. So that's why, therefore, these information, the spatial variation of this magnetic field strength, can give you information about the uh, orientation of the magnetic field with respect to the line of sight. Now with that, we would like to go into the linearly polarized fraction. So this is the linearly polarized fraction variation of that. So again, these are the 6 different frequencies bands and the time. And as you can see here, the linearly polarized fraction goes up to 12%. And also at different frequency band, it is very, very different from each other. And also if I take a cut across this and then show you the temporal variability, you will see that very close by frequencies are showing so this green line and the blue line are the very close by frequency. And if you can see here that these two lines are like tracing each other very closely. Whereas if you see the red line, which is separated by separated in the frequency, so that is no longer tracing the other two lines. So which means that as you increase the frequency separation, the temporal variability of each of these each of the frequencies are changing. Now, when we looked at the variability of the source morphology, these are the again same set of plots, but the upper panel is showing for the Stokes I, Stokes Q, and the Stokes U. And as you can see here that In the Stokes eye, again, we do see the variability in source sizes as well as their locations. But when it comes to Q and Q, the variability is much higher. But very interesting to show here that even if at different frequencies, the variability, the Stokes Q signature as well as U signatures are very different from each other. But if you look at just one frequency, let's say this one, you don't see any changes of the signature, the positive negative signature to occur here. And also same for here. So there, even these are two different bipolar signatures close to each other, but they are not changing across time. Whereas we do see a fit comparatively higher variability in the Stokes U images. Now, if you look at the polarization angles, which you compute from the Stokes Q and U images. So in that case, again, you do see that there is a change of polarization angle within different frequencies. But when it comes to a single frequency band, the polarization angle doesn't change during the emission of the type 2 burst. Now, this is puzzling because, first of all, we don't expect the linear polarization to be there at the first place. Why? Because if the polarization has emitted during has originated during the emission of this type 2 burst, so at this location the magnetic field strength is very high, and therefore there would be enormous Faraday rotation, and therefore no linear polarization should be the linear polarization should be completely washed out. But we do see here linear polarization, and we also don't see any change of polarization angle across the duration of the type 2 burst, which is telling you that after the generation of this linear polarization, there was effectively no Faraday rotation which has occurred of this linearly polarized emission. Now, if I'm to show you the spatial variation of the linearly polarized emission, so these plots are basically showing you the spatial variation where each of this row are again different frequencies, and the column are showing different timestamp. And this is the color is basically showing you the polarization angle, and this white color showing you the Stokes Q contours, and the cyan color shows the Stokes U contours. The negative are the dashed one, and the positive are the solid contours. So if you see here, so what I want you to notice here is this one, where you would find, so this is the one where there were two bipolar structure close to each other. And if you look at the time, its temporal variation, even though individual Stokes Q and U sources, they have changed their morphology, but the location at the polarization angle is always consistent with the location of the source. So which tells you that this polarization angles is indeed an information is associated to the local environment of the source region. So now the question is, what can give rise to this linear polarization? And another important thing is why this linear polarization has survived so far. So we started to look at that, and the first question that came to our mind, which is that either it has to be intrinsic or it has to be from the propagation effect. So as I already told you that if it is an intrinsic, then because of the high Faraday rotation, the high Rm at the emission site, this emission should be the linear polarization should be totally washed out, and therefore you should not see any linear polarization. So therefore, the linear polarization that we are seeing here is coming from the propagation effect, has to come from the propagation effect. Now, we have already seen that the polarization angle doesn't change much across the duration of the burst, which again tells you that there is the effective Faraday rotation is very, very negligible after the generation of the linear polarization. Now, when that would happen, if if the linearly polarized emission has generated at a higher height in the solar corona, where after which there is no effective Faraday rotation, or let's say the effective Faraday rotation is very negligible. So now if that is the case, then we have to keep the have the linear polarization has to originate from a solar height which is greater than 3.1 solar radii. Now there are recently a few reports where linearly polarized emission has been observed from stellar radio burst, as well as there is one report which says linearly polarized emission has been reported from type 1 and type 3 radio burst in this metric wavelength. And out of this, all these reports have there are two possible scenarios which has come out from these reports. One is that the reflection from the overdense region, which means that if the emission has occurred while this was propagated, this has been reflected from an overdense region in a higher height, and then so reflected by a Brewster angle, and therefore the linear polarization has been originated, and uh, therefore we do see it. While this makes sense because in this case, the emission would be at higher height, but the kind of morphology and the variability that we see in the Stokes Q and U sources, and also the two consecutive sources, the positive and negative sources, these cannot come from, these cannot be explained from this scenario. So then we move on to the other scenario, which is the mode coupling from by the quasi-transverse propagation. What does that mean? So when an electromagnetic wave propagates through so quasi-transverse means when the electromagnetic wave is propagating perpendicular to the magnetic field. So what is mode coupling? So as you know, that when an electromagnetic wave propagates through a magnetic field, it basically split into the X mode and O mode. Now, during its propagation, under some so during its propagation, it may change energy between the X mode and O mode, and this phenomena is called as mode coupling. So we typically use a mode coupling parameter, which is known as Q. I'll talk about it in a minute. But so this Q parameter basically decides so what is the mode coupling regime through which the propagation is through which the emission is propagating. So when Q is very, very less, which means the weak coupling regime, which means this X and O mode will independently propagate. If Q is very, very greater than 1, which means strong coupling regime, which means that this X and U, X and O, this will be tightly coupled, and therefore, even if there is any magnetic field, that will not affect these two X and O mode. So which means the polarization is frozen. And then there is the transition region. So the transition region between the weak and the strong coupling, where partial energy transfer can occur between the X and O mode, and therefore which can generate the linear polarization. Now, this is typically the how the coupling ratio, the Q parameter is defined, but I won't go to the details of it. But what I want you to remember is that uh, there are there are many reports which has shown that under particular scenarios, in the meter wavelength, there can be moderate to strong coupling medium, which means that in this height of the solar corona, the two solar radii and so on, there also we do expect moderate to strong coupling regime to be there. So now, which means that after the generation of the type 2 emission, it can encounter strong or moderate or strong coupling regime, even if it has started from a weak coupling regime. So just to give you an schematic scenario, so let's look at this. So let's say this is a shock and this is the type 2 emission. And now this is the type 2 emission, and let's say these are the different coupling layers. So this is the weak coupling layer, the transition region, and the strong coupling layer. And as you can see here, because the magnetic field structure is very complicated at the lower coronal height, so there may be multiple encounters where the QT propagation is happening. And therefore, we think that it may happen that the emission started from a weak coupling regime, then it went to the transition regime where the linear polarization has been generated, and after that it has encountered the strong coupling regime, which means now the whatever the polarization state was, that is frozen, and therefore this frozen information we are getting, what we are seeing here. So this scenario basically tells us that how the linear polarization can be possibly can generate and also can survive through this coronal medium. However, this is again a possible scenario, but yes, we can discuss or more explore more scenarios which can again explain the information, the results. So here are the key takeaways. As I said, so this um, spectro-polarimetric imaging studies of solar radio burst are very, very important because it is one of the because this will give us many, many information about the local plasma density, which and the magnetic field, which may be washed out because when we take a dynamic spectrum based information. For this particular one, so in this study, this is the most detailed polarimetric study of a type 2 burst so far. We have shown the spatially resolved measurement of the magnetic field strength as at the shock location. We have demonstrated that how dynamic spectrum based studies may underestimate the magnetic field strength. And we also have shown that this is the first detection of the linear polarized emission from a type 2 solar radio burst, which can go to 12%. And in our study, we have found that the polarization angle varies across frequency, but during the type 2 burst, duration of the type 2 burst, it is almost stable. And if we want to understand or let's say explain what can give rise to this, is mode coupling during the QT propagation could be one of the possible mechanism for the generation and the survival of the linearly polarized emission from this type 2 burst. So with that, I would like to end here. Yeah, thank you.
Thank you very much, Puja. This was a great, very interesting presentation. So let's open the floor for questions. Let's see, do we have a question from the audience? Maybe I can start with a couple of questions if you don't mind.
Yeah, sure.
So first question is, can you say a few words about how the magnetic field is estimated from the circular polarization?
Okay, sure.
And the second question is, have you checked that how this linear polarization behaves as a function of frequency? Because from that slide 17 that you showed, it seems like for the you would get much more signal at the lowest frequencies, much more linear polarization because the frequency of emission is lower, right? Where the shock wave is higher up in the solar corona, whereas at the highest frequencies that MWA observes, you would not get a high Q parameter value.
Okay.
Does that make sense?
I'll start by answering your first question, but I'm
Sure.
not sure if I understood the second question.
Sure. Let's go through the first one.
Okay. So this is the formula which has been used to estimate the magnetic field strength. So the information that goes into it is that first of all, because the okay, so the idea is the polarization, the degree of circular polarization of the harmonic emission would be proportional to the plasma frequency and the gyro frequency. So this FB is the gyro frequency and the plasma frequency. So these are the two information that goes into it. And then this theta. Theta is basically the angle between the line of sight and the magnetic field direction. So these are three information that goes into it. So, so even though at the same height, at the same frequency, we don't expect the FP to vary, and also because the extent is very uh, compact, so which means the gyro frequency, the strength of the magnetic field should not vary that much. So the only thing which can vary is the theta, the angle between this angle between the line of sight and the magnetic field, uh, and which we think is giving rise to the spatial variation. Yeah, and if you does that answer your question?
Yeah, I think so. Thank you. And
Yeah,
maybe we can go to slide 17 so I can explain the second question.
yeah, sure.
Okay. So if you want linear polarization to survive, the Q parameter must be bigger than one, right? Much
Yes.
bigger, right? So, and that would happen higher up in the corona. So naturally, you would expect to see more linear polarization at the lower frequencies as opposed to the higher frequency, right? Higher frequency. So if you are able to image between 300 or 250 megahertz and 80 megahertz and see
Mm-hmm.
how the degree of linear polarization changes,
Mm-hmm.
you could you could perhaps confirm this
Yes.
theory.
Yeah, but unfortunately for this particular event, half of the spectral band was the data was good, so therefore we could not go for the higher frequencies. But yeah, I think one can also, like, when we have a higher spectral coverage, in that case we can definitely look at it. But so far the six bands that we have, so there if you see here, we don't see any variation of um, let's say monotonic variation or increase or decrease with frequency. It seems like in the middle frequency, in these frequencies it's higher as compared to the highest and the lowest frequencies.
Okay. Okay. Thank you. Oleg, you had a question?
Uh, yes. No, do you hear me?
Yep.
Yeah.
Yep.
Uh, so thanks, Puja. That's an interesting, formidable presentation. Although I skipped a couple of the first slides, so had another meeting. I have a couple of general questions because kind of on just technically, if we think on circular polarization versus linear polarization, and the question here is kind of the circular seems to be more standard handle of the line of sight field for plasma emission, and linear is much more harder to detect, if I'm right. It's not quite my field, just asking, and interpret because of further rotation through the turbulent corona kind of tends to wash it out. And here is the question: if we report and talk about linear polarization, which is hard to preserve through the corona. What is the upper limit? I mean, it's some kind of derivation. How does it imply for unusually low turbulence or short path lengths to the source? How does it work technically? And on a more kind of wide perspective question, maybe it's a question more suitable for more general panel discussion, but more complementary with our domain. So if those radio-derived B fields could be a strong external constraint actually for MHD and an apparent type of shock and particle acceleration modeling, so the polarization gives the field the shock, which is exactly the quantity that governs perpendicular, quasi-perpendicular versus quasi-parallel acceleration. Is that right to say this? Is it the right conclusion in that sense?
Okay, so you
Let's split. Let's talk linear polarization. How do we what limits are there?
Okay.
What is the upper limit, basically?
Okay, so, sure. So, okay. So right now the way as you already know, the Faraday rotation at the lower coronal height is very, very high. So therefore it will, because there are differential Faraday rotation, this will depolarize the linearly polarized emission, right? So
Mm-hmm.
therefore, if you want to preserve the linearly polarized emission, it has to be um at a region where this differential Faraday rotation is very less or negligible. Otherwise,
Mm-hmm.
the linearly polarized emission would not survive. Now, there could be two possibilities. One, if the linearly polarized emission is occurring at a higher height in the solar corona, after which we like we so as you have seen that this is 160 kilohertz image frequency resolution images, right? So
Mm-hmm.
if the Faraday rotation is such that within the 150 160 kilohertz band, it is depolarizing the linear polarization. So therefore, we don't expect it to see, right? So therefore, one is that within this 160 kilohertz bandwidth, it has to survive. For that, the linear polarization has to occur at a higher height. Or the second possibility, which I was discussing here, that if after the generation of the linear polarization, it has gone through a medium where it is Q is very, very greater than 1, which means strong coupling regime, which means whatever the polarization it has been generated in that medium, it will be preserved throughout the propagation. There would be no effect of the magnetic field, of the background magnetic field. So I think these are the two scenarios which I could think of which can uh, make the linearly polarized emission survive. But now the question is, like, how much of the linear polarization would survive? So that I think um, that is a bit difficult to say from these emissions because we don't know what to expect. So therefore, because there are already a lot of propagation effects which has been introduced to the Stokes V during the propagation, so it's a bit difficult to say. But one could also do some kind of experiment where they initiated some simulations where they looking for this propagation effect. So let's say we started with 100% circularly polarized emission, and now if these are the conditions, how much polarization should we recover? Do we see any linear polarization or not? So these kind of things one can play around. But yeah, does that answer your question?
Yeah, it does more or less. Well, kind of provokes a long discussion in my mind. Yeah, but it does things.
Okay. Okay. Yeah, I think there was another second question, which
Mm,
in no.
well, just the second question. Probably we could. I don't want to take the whole ground. Probably we can drop it, or maybe someone
Yes,
can
maybe
elaborate on
we
that.
can discuss it offline as well.
Or probably offline. I don't know. Because it's just the question. I'm just wondering how it could be connected to other things that we are doing. How it could put constraints further. Well, obviously it could for MHD parent type of shocks and kind of particle acceleration modeling. So as if the polarization gives you the field at the shock, so this is kind of exactly the quantity that, I don't know,
Mm-hmm.
drives or governs this quasi-perpendicular versus quasi-parallel acceleration.
Mm-hmm.
Um, so maybe if you can comment on that,
So this
just
type 2 emission,
just thinking out loud.
yeah. So uh, so the condition for the generation of this type 2 emission is basically when the shock is quasi-perpendicular to the shock,
Mm,
and also the shock has to be supercritical. So
mm.
because of that geometry, this non-thermal acceleration happens and the type 2 emissions occurs. And therefore, to me, it feels like there are more possibility to encounter this QT propagation. But yeah, but I'm not very aware of the uh, Yeah, I mean that is something that I could say right now.
Mhm. Okay, thank you. Maybe to be continued. Thanks a lot.
Yeah, thank you.
Okay, other questions? I have one more question, if you don't mind.
Yeah, sure.
Um, how would the results change, do you think, or would they improve or not if you increase the frequency resolution? In other words, if you instead of 160 kilohertz channels had, I don't know, 40 kilohertz or something. Do you think anything would change in terms of the result? Would there be enough polarization signal?
Okay. Okay. So for the frequencies where the bands where we are seeing higher polarization, certainly there, if you go to the 40 kilohertz, I mean, if you increase the resolution, uh, what we the absolute flux will decrease definitely, but I don't think that will change the results so much because we have made 160 80 kilohertz images and we don't see any kind of changes there also, and therefore we have gone to 160 kilohertz so that we don't lose any information as that at the same time we are I mean computationally capable of making those images, so it's a kind of optimization, but the results would not change.
And one more question that's related to LOFAR. So, if we, according to theory, of course, we're expecting to see better mode coupling, right? Better, higher values of this Q parameter higher up in the corona, then you would expect to be able to observe even more of this linear polarization signature with LOFAR observations, with the LBAs, right? So below 80 megahertz, because the CME, the type 2 emission is even higher up in the corona.
Mhm.
Do you expect that to be the case?
um, okay. First of all, the when I say the Q, um, okay. So when I say the Q has to be like at the higher height, there are strong coupling regime. So these are some scenarios which has been proposed. So when the magnetic field structures are very complicated, so that the length scale over which it is changing the orientation is very quick. So therefore, so um, these are some of the reasons for why the Q is very higher than one. Now, what I am wondering that these complicated magnetic field would we get at a very lower frequency, the higher height? If the magnetic field structure is something which can lead to this Q very greater than one, in those cases we do expect the linear polarization to see linear polarization at least. But again, this is a single study. So just taking one type 2 emission, we have tried to give into theory. I mean, tried to explain the possible scenario. But it's very important to look at more emissions, plasma emissions, so that we can have a like better understanding of the scenario. So I think at this moment, uh, expecting something from this is a bit thinking louder.
Hmm. Okay. But it doesn't hurt to try.
Yeah, sure. I think for that, I think we have to do polarimetric imaging study with LOFAR as well, and also more sample of type 2 or type 3, type 1 burst with MWA so that we can get more understanding like how do they change or do we see any frequency dependence properties or not.
Hmm. Okay. Thank you.
Yeah.
All right. Any final questions? No. Well, in that case, thank you very much, Puja, for this very interesting talk and this very nice study that you've done. And I hope you're enjoying our visit to
Yes,
Bulgaria and to the Rojan Observatory. And thanks everyone for also joining us as well
yeah.
today.
Thank you so much, everyone.